Hello everyone. Having discussed analysis of crystals, that is analysis of unit cell, now we are going to discuss some numerical problems based on this unit cell analysis. So let's discuss some problems based on this analysis of crystals, how the formulas or the concepts given in analysis of crystals can be applied in solving numerical problems. So let's take up some examples here. Gold crystallizes in FCC lattice, phase center cubic lattice having radius 0.144 picometer. Then what is the edge length of the unit cell? So question says element gold, this crystallizes in phase center cubic lattice such that the radius of gold atom is 0.144 picometer. Then what is the length of the unit cell? So says radius is 0.144 picometer. 1 picometer is equals to 10 to the power minus 10 meter. Now unit cell is given as phase center cubic lattice. So phase center cubic lattice, the relation between the radius and the edge length, that is 4r is equals to a root 2. So a root 2 is phase diagonal. So relation between radius and edge length for an unit cell of phase center cubic, that is 4r is equals to a root 2. Now we have to find the value of a. R is given, so therefore a is equals to 4 times r divided by root 2. So we are given the values of radius 4 into 0.144 divided by root 2 is 1.414. So this gives you the edge length of the unit cell of gold, in which radius of gold is 0.4144 picometer. So the basic point here is that we use the relationship between radius and the edge length of an FCC lattice. Next question. I can take the same question. Gold crystallizes in FCC lattice with edge length N A equals to 4.070 angstrom. Atomic mass of gold, this is given as 197. So gold crystallizes in FCC lattice which edge length A equal to 4.070 angstrom. Mass of gold is 197. What is the closest distance between gold atoms? What is the closest distance between gold atoms. So question says gold crystallization FCC with air length 4.070 angstrom. Then what is the closest distance between the gold atoms? So again question says we have an FCC. So for FCC type lattice, the closest distance between any two adjacent atoms or distance of closest approach. Distance of closest approach, that is the closest distance between any two adjacent atoms. So this distance of closest approach, that is dt. So d is equals to half of phase diagonal. So half of phase diagonal, that is phase diagonal is a root 2. So the distance, closest distance between any two adjacent atoms in FCC is half of the phase diagonal, that is a root 2 by 2. Therefore, the closest distance, this is a root 2 by 2. So A is given as 4.070 angstrom. So we have 4.070 angstrom into root 2 is 1.414 divided by 2. So this must be in terms of angstrom. So this is the closest distance. So the formula to be used is this relationship. The closest distance between any two atoms in an FCC lattice. Next question. A metal M, suppose we have a metal M, this metal M crystallizes in FCC and the BCC lattice. So we have a metal, this metal M crystallizes in two cubic lattice. One is FCC lattice, the other one is BCC lattice. So when this metal crystallizes in FCC lattice, the edge length of the unit cell is 3.5 angstrom, and when this same metal crystallizes in BCC lattice, the edge length is 3.0 angstrom. Then the question says calculate the ratio of densities. The ratio of densities of the metal in FCC to that of BCC. So crystal lattice is given. One is FCC lattice, the other one is BCC lattice. Edge length of FCC is 3.5 angstrom. Edge length of BCC is 3 angstrom. Then we have to find the ratio of densities. So since the question revolves around density, so we have to use the unit of formula of density. Density rho is equals to Z, that is effective number of atoms per unit cell, molecular mass divided by A cube times Avogadro number. So A is given here, that is Avogadro number, which is a constant. Z for FCC and BCC, we have to find the values of Z. So therefore there is density of the metal in FCC to that of BCC. So this equals to Z of FCC into molecular mass divided by A of FCC cube into Avogadro number divided by density of BCC. So this is Z of BCC into molecular mass divided by A cube of BCC into Avogadro number. So therefore this comes out to be, look at this, M by NA, this will cancel out. So what is that is Z of FCC divided by Z of BCC into A cube of BCC divided by A cube of FCC. Effective number of atoms in FCC that is 4. Effective number of atoms for BCC that is 2. A cube of BCC that is 3. So 3 into 10 to the power minus 10 divided by FCC 3.5 into 10 to the power minus 10 cube. So 10 power minus 10, 10 power minus 10 will cancel out. So this comes out to be 2 into 3 cube 27 divided by 3.5 cube. So this is the ratio of densities of the metal in which the metal crystallizes in FCC with as 3.5 as well as BCC with as 3. So formula to be used is density, which is equals to Jm divided by A cube by Avogadro number. Next question. Silver metal Ag crystallizes in FCC. So we have this metal M crystallizes in FCC cubic lattice with S length E equals to 4.07 into 10 to the power minus 8 centimeter. So S length of FCC unit cell is 4.07 into 10 power minus 8 centimeter, and density equals to 10.5 gram per centimeter cube. Then what is the atomic mass of silver? Atomic mass of silver. So question says, what is the type of lattice? That is FCC lattice. What is the S length? That is given. What is the density? That is given. So what we have to find out is atomic mass. So we have the density. So density rho is equals to Jm divided by A cube into Avogadro number. So if you look at this equation of density, density is given in S length is given Avogadro number, this is the constant. J is fixed for this FCC lattice. So what is that is n. So therefore this molecular mass or the atomic mass of silver, this is density A cube Avogadro number divided by J. Density is given as, so therefore M is density. Density is 10.5 gram per centimeter cube. A cube, that is 4.07 into 10 to the power minus 8 centimeter cube into 6.02 into 10 to the power 23, that is Avogadro number, divided by Z. For FCC, effective number of atoms per unit cell is 4. So this gives you the gram atomic mass of silver. So So if you simplify this will come around 108. So 108 is the gram atomic mass of silver, 108. So this is how we have to find the mass from density S length A. Next question. Niobium is a metal crystallizes in body center cubic lattice type with density equals to 8.55 gram per centimeter cube. What is atomic radius? What is the atomic radius of this element niobium if atomic mass of niobium is 93 U. So we have an element niobium. This niobium crystallizes in BCC lattice. The density is 8.55 gram per centimeter cube. Atomic mass is given as 93 U. Then what is the atomic radius of the element niobium? So again the question revolves around radius. So we have to use the equation of radius. So density is equals to Z n divided by A cube and N. So N is given, M is given, Z given, density given. So what we have to find out is A. So therefore A is equals to Z M divided by density into Avogadro number cube root. So therefore look at this, A is equals to Z for BCC, Z equals to 2. So we have 2 into mass, that is 93. So gram atomic mass of the element is 93 gram divided by density is 8.55 gram per centimeter cube into 6.02 into 10 to the power 23. So 1/3. So this is the S length. So this must be in terms of centimeter. So we have this S length. Now the crystal is BCC. Now for BCC, the relationship between the radius and the S length is 4 BCC. We have 4 times radius is equals to the body diagonal, that is A root 3. So from this we will find the values of R. So therefore R is equals to A root 3 by 4. So we have the values of A. The root 3 is equals to 1.731. So we'll find the values of radius. So first, from this density, we have to find the values of S length, and from this S length, we have to find the values of the radius R. That is the relationship between the radius and the S length of an BCC type crystal. Question says the element titanium crystallizes with density of 4.54 gram per centimeter cube, having the S length of 412.6 picometer. Then question is, in what cubic lattice the element titanium crystallizes. Atomic mass of titanium, this is given as 48. So question says we have an element titanium. This titanium crystallizes in some cubic crystals. The density is given as 4.54 gram per centimeter cube. The as length of the cubic that is 412.6. Then the question is, what is the crystal? Is it PCC type? It is simple cubic type? It is hexagonal type? Or it is body center type? Now, to define this type of cubic lattice, what we require is we have to find the effective number of atoms. If the effective number of atoms comes out to be 1, then this comes out to be simple cubic. If effective number of atoms, that is ring, comes out to be 2, then it falls in BCC type. If the effective number of atoms per unit cell falls in 4, then it comes under FCC type. So we have to find the value of J. So density is given, S length given, atomic mass is given. So we have this density J n divided by E cube, Avogadro number. So density S length mass is given. You have to find the values of J. So J is equals to density A cube E by M. So we have to look at this density is 4.54 gram per centimeter cube. S length is given in terms of picometer, so this must be converted in terms of centimeter. So this is 412.6 into 10 to the power minus 10 centimeter cube. Avogadro number 6.02 into 10 to the power 23 divided by gram atomic mass, that is 48. So on solving this, we'll find the values of J. So depending on the values of J, we'll classify the cubic crystal in which is titanium. So look at this. If Z equals to 1, that is simple or primitive unicell. If Z equals to 2, then this is BCC. If Z equals to 4, then this is FCC. So depending on the values of J, we will classify whether this titanium falls in FCC, BCC or FCC. One more question here. The S length of a BCC metal crystal, S length of a BCC metal crystal is 352 picometer. The S length of a BCC metal crystal is 352 pm. Then what is the radius of the metal? Question says we have a metal. This metal crystallizes in BCC type lattice, and the S length of initial is given as 352 picometer. Then what is the radius of metal? So we have this term BCC. So for BCC, the relationship between the S length and the radius. So for BCC type crystal, where this relationship 4 times radius of atom or sphere is equals to body diagonal. So we have this S length. So therefore, the radius of atom is equals to A root 3 by 4. A is 352 picometer. The root 3 is 1.73 divided by 4. So this must be in terms of picometer. This is the radius of atom. So this is the radius from S length provided the type of crystal is mentioned. So BCC 4 times radius is equals to body diagonal. For FCC 4 times the radius is equals to face diagonal. One more question is, an element with density of an element is 6.8 gram per centimeter. So we have an element with density 6.8 gram per centimeter cube. This crystallization body center cubic tab having S length A equals to 290 picometer. Calculate the number of atoms in 200 gram of the element. So we have a metal or atom. So we have an element with crystallization BCC having density 6.8 gram per centimeter cube. S length of cubic cell is 290, and total mass of the sample is given as 200 grams. So how many atoms of the element is present in the sample? So question says BCC. So for BCC, Z equals to 2. Density is given. So density is equals to Z m by A cube, Avogadro number. So in this equation, we know the value of Z. We have A, we have Avogadro number, we have rho density. Then what is that is mass, that is gram atomic mass. So gram atomic mass is equals to density A cube divided into Avogadro number divided by Z. So putting the values of density A and Z, density is 6.8, A is 200 picometer, 90, that is should be converted into centimeter. So 290 into 10 to the power minus 10 centimeter cube. Avogadro number 6.02 into 10 to the power 23 divided by Z, that is 2. So we have this, the mass of the element. So this is the gram atomic mass. Let this value be x. So we have a gram atomic mass. Gram atomic mass is the mass of 6.02 into 10 to the power 23 atoms. That means in the gram atomic mass of any given substance, how many atoms are present? 6.02 into 10 to the power 23 atoms are present. So therefore look at this. X gram, that is gram atomic mass of element contains 6.02 into 10 to the power 23 atoms. Then question says, how many atoms are present in 200 gram of this thing? So 1 gram of the element will contain 6.02 into 10 to the power 23 divided by x. So 200 gram of the element will have 6.02 into 10 to the power 23 into 200 divided by x. So we have the values of x. So this is the values of x. So therefore n number of atoms, that is 6.02 into 10 to the power 23 into 200. The value of x is 3.4 into 290 into 10 to the power minus 10 cube into 6.02 into 10 to the power 23. So again this term cancels out. So this is the value of the number of atoms present in 200 grams provided with this data. So these are the problems, some of the problems in which the various terms that we use in analysis of crystals like density, radius, distance of closest approach, coordination number, etc. as length. So this is how we use those formulas in solving numerical problems. Having learned this unit cell dimension, let's define the unoccupied space present in a unit cell, that is void. Voids. So void stands for unoccupied space in the closed packed structure. So we have a unit cell. In this unit cell, we have different atoms are placed in a different manner. So these atoms or these spheres will occupy certain volume. After this, some of the space is left unoccupied. So that unoccupied space is what we call as void or voidal space, and these voids, this is also known as interstitial sites, that is left unoccupied by spheres in the unit cell. So we have to find this void and how many types of void and the location of voids. Now these voids is of two types. One is known as tetrahedral void and the other one is octahedral voids. So closed packed structure, that is CCP or FCC, and HCP, hexagonal closed packed structure. We find two types of voids. One is known as tetrahedral void, the other one is known as octahedral voids. So tetrahedral voids means the unoccupied space is surrounded by four spheres, that is coordination number is 4. Octahedral voids, the unoccupied space is surrounded by 6 spheres, that is coordination number 6. So we'll take up one by one octahedral voids and the tetrahedral voids. First take up these tetrahedral voids. Now in tetrahedral voids, we have 3 spheres forming an equilateral triangle. Now when these 3 spheres forming an equilateral triangle, there is a depression. Above this depression, a sphere is placed. A sphere is placed above this depression. So we have 3 spheres forming an equilateral triangle in which there is a depression. Above this depression, we place another sphere. So when we place these 4, then there is an unoccupied space between these 4 spheres. These unoccupied space or interstitial site, this is in contact with 4 spheres 1, 2, 3 and 4. So these unoccupied space, this is what we call as tetrahedral voids. Why this is known as tetrahedral voids? Because if we join the centers of these four spheres, it forms a regular tetrahedron. So we have an equilateral triangle, three spheres are placed here. Depression, above this depression we have another fourth sphere. So this is the point, this is tetrahedral. So exactly at the center of tetrahedral we have a tetrahedral voids. So this is the meaning of tetrahedral voids. Now we have to locate these tetrahedral voids. The location of tetrahedral voids. Now for this location of tetrahedral voids, we'll take the help of FCC lattice. Let's consider an FCC lattice, face center cubic lattice. So we have a cube. Now let's bisect this cube into 8 mini cubes. We'll bisect this cube into 8 mini cubes. So we are bisecting a bigger cube into 8 mini cubes. Now let's consider this to be the origin of the FCC. So we have an atom here. Let's consider this to be the origin. So we have. Now since we have an FCC, these corner atoms will be in contact with face center atoms in which having this common point. So we take this face, so we have a face center atom here. So these face center atom and corner atom of this face will be in contact with each other. Similarly, the bottom face, this face center atom of this bottom face will also be in contact with this corner atom. And similar to this front face, we have this face center. So these face center atom will also be in contact with this corner atom. So considering this to be the origin of the face center cubic lattice, we have a sphere. This sphere occupying this corner will be in contact with those face center whose faces are joined with this common. So we have three faces. This left face, front face and the bottom face. So we have this. Now since this corner atom is in contact with this four face center atoms. If we join all these, then we'll get a regular tetrahedron. So let's do this. So joining all these four atoms, we get a regular tetrahedron. So since we are having a regular tetrahedron, that means the four atoms are in contact with each other. That means we are having a regular tetrahedron. So exactly at the center of this regular tetrahedron, we have a tetrahedral void, which is exactly at the center. So this is tetrahedral void exactly at the center of mini cube. So we have a mini cube. So exactly at the center of this mini cube, we have a tetrahedral void. So this is the mini cube. So we have this mini cube. In this mini cube, we have a regular tetrahedron in which the corner atom is in contact with three face center atoms, forming a regular tetrahedron. Exactly at the center of this tetrahedron, we have a tetrahedral void. So look at this. One mini cube contains one tetrahedral void. Since there are total 8 mini cubes, so how many tetrahedral voids will be there? 8. So therefore, since each mini cube contains one tetrahedral void, location is exactly at the center of the mini cube. Since there are 8 mini cubes, there are a total of 8 tetrahedral voids in an FCC lattice. So we are considering FCC lattice. So when this FCC lattice is divided into 8 mini cubes, we found that each mini cube contains a tetrahedral void. Since there are 8 mini cubes, so a total of 8 tetrahedral voids present in FCC. So therefore we have this FCC. For this FCC, number of tetrahedral voids is equals to 8. So number of tetrahedral voids is 8. So this can be written as 2 into 4. Now we are considering FCC lattice. For this FCC lattice, effective number of atoms per unit cell is 4. So we can write down this is 2 into Z. So for FCC, number of tetrahedral voids is 8. Location is actually center of mini cube. So number of atoms per unit cell of an FCC is 4. So we can write down total number of tetrahedral voids is 2 times J. This is tetrahedral void. So we have this. Therefore, look at this. Generalization is number of tetrahedral voids in a closed tank structure is always 2 times effective number of atoms per unit cell. So once we know the type of unit cell, we can define Z. Once we define this Z, we can easily define the number of tetrahedral void, that is 2 times Z. So we have this. So these tetrahedral voids as I have given you location. Location is, so we have this center of cube. Similarly, the diagonal opposite center cube of this will also have another tetrahedral voids. So location is two tetrahedral voids along each body diagonal. So there are two tetrahedral voids per body diagonal. So in a cube, how many body diagonals? So look at this. This is one body diagonal, second body diagonal, third body diagonal, fourth body diagonal. So in a perfect cube, there are four body diagonals, and each body diagonal contains two tetrahedral voids. Number of body diagonal is equals to 4 in a cube. So we have this number of tetrahedral voids, location. Now let's come back to this. So we have this unit cell. Now let this be the position of host atom. Now we have this body diagram. This is one of the body diagram. Now in this body diagram we have two tetrahedral voids. So we have a tetrahedral void here. Similarly, we also have a tetrahedral void here. So let this be A. This is A. This is B. Let this point be A prime. This point be B prime. This is host atom, and this is tetrahedral void. Now we have to find the distance. Let RH be the radius of host atom and RT be the radius of tetrahedral void. This is the host atom, this is tetrahedral void. Now we have to find this. So RH plus RT, this comes out to be 1/4 of body diagonal. If we assume the edge length of this unit cell, that is A. So look at it. That is A, B. This distance is A root 3. This is A root 3 by 4. This distance is also A root 3 by 4, and this distance A prime, that is A root 3 by 2. That means we have this AB, that is body diagonal, A root 3 by, A root 3. A prime is equals to B prime. This is equals to 1/4 of body diagonal A prime B prime is equals to half of body diagonal, and this is the distance with, so this distance, this is total body diagonal, which is 1/4, this is 1/4, this is half, this is 3/4. If this is one total, then this is 1/4. This distance AB prime is equals to A prime B prime. So again, A B prime is equals to A prime B. This distance is equals to 3/4 of body diagonal. The body diagonal is A root 3. This is 3/4, 1/4. So total is 1. So this is the host atom with radius RS. This is tetrahedral void. So distance between a tetrahedral void and the host atom, this is 1/4 of body diagonal. If this is the case, look at this. The closest distance between two tetrahedral voids. Distance between two tetrahedral voids. So if this is the host atom tetrahedral void, distance is 1/4 of body diagonal. This is tetrahedral void, this is also tetrahedral void. So the distance between two tetrahedral voids, this distance is equals to A prime B prime. So A prime B prime is equals to A root 3 by 2. So the distance between any two tetrahedral voids in an FCC is A root 3 by 2. This is the distance between two tetrahedral voids. This is the distance between host atom and tetrahedral void. And these are the various distances that I have shown you. So this is the location of tetrahedral voids in an FCC. So number of tetrahedral voids in FCC is 8. So this can be written as 2 times J. So generalization is total number of tetrahedral voids in a closed package structure is 2 times Z, where Z is the effective number of atoms per unit cell. Location is exactly at the center of 8 mini cube. So since there are 8 mini cubes, we have 8 tetrahedral voids. So location is 2 tetrahedral voids along the body diagonal. Since the number of body diagonals in a cube is 4, so there are total 8 tetrahedral voids in a FCC. This is about tetrahedral voids. Now, once we know the now second is location of octahedral voids. In an octahedral void, the coordination number is 6. That means that particular voidal space will be surrounded by 6 spheres, something like this. There is an octahedral. This is formed by placing two equilateral triangles opposite. Now, we have these two equilateral triangles placed in opposite direction, distribution of octahedral. If you place spheres at the, we have three spheres occupying this equilateral triangle. When you place this exactly at this point, you have one octahedral void. That means three spheres forming this equilateral triangle, another three spheres forming of that equilateral triangle, and they are placed in such a way that in between these six two there is an octahedral void. So this unoccupied space is in contact with six spheres, so this coordination number is 6. So we have looked at it. This is an equilateral triangle, regular octahedron. Exactly at the center of this, we'll have one octahedral void. So we have to find the location of these octahedral voids in FCC lattice. So we have this FCC lattice. Now in FCC lattice, atoms occupy corners as well as face center, subject to the condition that each corner atom, that is, two adjacent corner atoms should not be in contact with each other, but the face center atom will be in contact with four corner atoms as well as the face center atom having common edge. So this was the condition for placement of spheres in an FCC lattice. Since these two adjacent spheres is not touching each other, that means there is some unoccupied space. Let a sphere be placed in between these two corner atoms such that this sphere touches these two corner atoms. If this sphere touches two corner spheres, this sphere will also be in contact with this space center atom, top as well as right inside. So that means this particular point is surrounded by six spheres: 1, 2, 3, 4, 5, 6. So this particular point is what we call as octahedral void. So in an FCC, at the center of an edge, there is always one octahedral void. So as far as location is concerned, so the first location is at the center of each edge. At the center of each edge, we have an octahedral void. So let's see the contribution of octahedral voids coming from this edge. So in a perfect cube, how many edges are there? 12 edges. 4 plus 4, 8, 9, 10, 11, 12. So contribution of each particular edge is the common property of 4 unit cells. So it will have a contribution of 1/4. So therefore, octahedral voids at the center of edges, number of edges 12. Each edge is a common property of 4 unit cells, so contribution is 1/4. So we have 3 octahedral voids present at the center of edge. Now again consider this. We have this. This is the face center atom of rear face. This is the face center atom of front face. This is the face center atom of bottom face. This is the face center atom of left face, right face, top. Now, considering this, exactly at the center of this cube, we will also have an octahedral void. This octahedral void present at the center of cube will be in contact with 6. We have 1, second sphere, third sphere, fourth sphere, and fifth, this is sixth. So the second location is at the center of cube. So at the center of cube, we have one octahedral voids. Along the centers of edge, we have how many octahedral voids? 3. Exactly at the center of cube, we have one octahedral voids. Therefore, total octahedral voids is 3 plus 1, that is 4. So in an FCC lattice, total number of octahedral voids is 3 along the centers of edge, 1 exactly at the center of cube, so total 4. So this can be written as 4. So 4 is effective number of atoms per unit cell for an FCC, so this can be written as Z. So therefore, in generalization, number of octahedral voids is equals to rank, effective number of atoms per unit cell for an closed packed structure. So number of octahedral voids is equals to rank, and number of tetrahedral voids is equals to 2 times rank. So this is the location of octahedral void along the centers of edge, along the center at the center of cube. Number of tetrahedral voids is equals to 2 times. So therefore, number of tetrahedral voids is equals to 2 times number of octahedral voids. So in a cubic lattice closed packed structure, total number of tetrahedral voids is 2 times number of octahedral voids. Total number of octahedral voids is equals to effective number of atoms per unit cell. Total number of tetrahedral voids is 2 times the rank. So therefore, total number of tetrahedral voids is 2 times number of octahedral voids. Or the ratio of number of tetrahedral voids to that of octahedral voids is always equals to 2. Now, number of octahedral voids in an FCC is Z. Effective number of atoms per unit cell is 4. So there is 1 octahedral voids per sphere. That is 1 octahedral voids per sphere. So there is 1 octahedral voids associated per sphere in a FCC lattice. Just look at this. Number of tetrahedral voids is 8. Effective number of atoms per unit cell is 4. So when we consider this, in case of tetrahedral voids, there are 2 tetrahedral voids per sphere. That means each sphere in an FCC is associated with 2 tetrahedral voids. So per sphere there are 2 tetrahedral voids. That means 1 above and 1 below. But in case of octahedral voids, 1 sphere is associated with 1 octahedral voids. In terms of location, octahedral voids is at the centers of edge and exactly at the body center. Now coming to the radius. This is octahedral void, this is host atom. If this distance, that is the S length, that is A, host atom, then now look at this. This distance 2 times the radius of host atom plus 2 times radius of octahedral void is equals to the S length. Look at it, this is octahedral void, this is host atom, or we can say the radius of host atom plus radius of octahedral void. This distance or distance between host atom and octahedral void is equal to half of its length. So this is the relation between host atom. This is radius of host atom, the radius of octahedral void. Distance between an octahedral void and a host atom is half of its length. We have this. Now let's find the distance between octahedral void and tetrahedral void. So we have an octahedral void here. If you look at this earlier structure, exactly at the center of this, we'll have one tetrahedral void here. If you consider this body diagonal, we'll have one tetrahedral void. This is octahedral void. This is tetrahedral void. This distance, this is octahedral void. This is tetrahedral void. Along this body diagonal, we have two tetrahedral voids. This distance, this is the distance between octahedral voids and tetrahedral voids. So RO plus RT, distance between octahedral voids and tetrahedral voids. This is 1/4 of body diagonal. The distance between octahedral void and tetrahedral void in an FCC like this is 1/4 of body diagonal. So this is about voids, types of voids, their location, and the parameters containing these voids. So generalized form is in any closed peg structure, number of tetrahedral void is 2 times Z, and each sphere is associated with 2 tetrahedral voids, and number of octahedral voids is Z, and each sphere is associated with 1 octahedral sphere, octahedral voids. Now, with this generalization, let's see. We have an FCC, so we have FCC like this. FCC Z equals to 4, so therefore number of octahedral voids is equals to Z, that is equals to 4. Number of tetrahedral voids is equals to 2Z equals to 8. So total number of voids is 8 plus 4, 12. HCP, hexagonal closed packing. This is also known as cubic closed packing because both have 74% packing efficiency and the same coordination number. And coordination number is 12 in both. HCP, hexagonal closed packing, the packing number of atoms per initial is 6. So number of octahedral voids is equals to Z equals to 6. Number of tetrahedral voids is equals to 2Z, this is equals to 12. And total number of voids is 6 plus 12, 18. This is the number of voids in a closed peg structure. Now, based on this, let me give you an example. A compound is formed between two elements X and Y. A compound is formed between two elements X and Y such that X occupies, X is cation, and this occupies octahedral voids. So we have a compound formed between two elements X and Y. X is a cation, and this cation occupies octahedral voids, and this Y is anion, and this anions form cubic closed peg structure. Cubic closed peg means this is nothing but the FCC. So what is the formula? What is the formula of the compound? Question clearly says Ni is forming FCC, the phase center cubic. So therefore look at this. Y effective number of Y FCC occupying corners as well as phase center. So this is J. This is equals to 4. So Ni occupying FCC, that is contribution of this Y Ni is 4. This X, that is cation, so effective number of X. X occupies octahedral voids. So number of octahedral voids in an FCC lattice, this is also equals to J. So this is 4. Number of octahedral voids is equals to J. This is equals to 4. Therefore, the formula of the compound is X4, Y4, and the simplest ratio is X1. Simplest the ratio. So this is how we define formula, provided we know the position of cations and anions in a cubic lattice system. So this is the location of octahedral voids, tetrahedral voids, and the calculation of number of tetrahedral voids and the octahedral voids in a closed peg structure. Now for this, we take the help of FCC lattice because FCC lattice is more convenient to define all these tetrahedral voids and octahedral voids. Now, while considering this, we are assuming that all these spheres placed in an unit cell are exactly identical. The size of spheres of O, atoms or spheres, is exactly identical. But we have ionic crystals. In ionic crystals, we have cation and anion, and the size of cation and size of anion is different. So when we considering the ionic crystals, so these ionic crystals having cation and anion having different radius, so packing of different spheres are involved. If the packing of different spheres are involved in an ionic crystal, so this relationship might change. So this packing efficiency, or how these cations and anions can be efficiently packed in any crystal structure, depends on the radius ratio. So for this we'll find the radius ratio. So we have a term radius ratio. This radius ratio is for ionic compounds having different size of cation and anion. The size of cation and size of anion are different, so we have to place this cation and anion in the crystal. So this involves different size spheres, packing of different size spheres. So this packing of different size spheres depends on the radius, the ratio. So this radius ratio RR, this radius ratio is defined as a radius of cation divided by radius of anion. So this is the radius of cation R plus radius of anion R minus. So this radius ratio will define what is the coordination number and how efficiently the crystal can be packed. Now look at this. Normally the size of anion is greater than size of cation. If the size of anion is greater than size of cation, in majority of the case, the anions will form the close packed structure, and Since the cation being smaller in size than that of anions, these cations will occupy the voids, that is tetrahedral voids or octahedral voids. So if the size of cation is more, if you increase the size of cation, the number of anions that will be surrounding this cation will be increased. That means increasing the value of this radius ratio means we are increasing the size of cation or decreasing the size of anion. The coordination number of the cation will increase. That means more anion will surround it, a larger cation than a smaller cation. So more is the value of radius ratio, more will be the coordination number. More is the value of radius ratio, more will be the coordination number. So on increase the value of radius ratio, coordination number of the crystal will also increase. This simple symbol. Okay. If the size of cation is very small, so only limited number of anions will surround this small size cation. If the size of cation is increased, more anions will surround this larger size. So as the size of cation increases, radius ratio also increases. As the radius ratio increases, the number of anions surrounding a cation will also increase. That is, the coordination number of cation will increase. So this radius ratio is not a fixed value. This is always a range. In that particular range, we'll have that particular coordination number. So for this, I'll just give you the range and the radius ratio. So that point is, what is radius ratio? That is radius of cation by radius of anion, and this is for ionic crystals having different size of cations and anions. Generally, anion being larger in size occupies or forms the closed pack structure. These cations being smaller in size occupies the octahedral voids or tetrahedral voids. Increasing the value of cation, the radius ratio will increase. If the radius ratio is increased, the coordination number of cation will also increase in the crystal. So this radius ratio is always a range. This is not always a fixed particular value, this is always in a range. So let's see this radius ratio. If the radius ratio is less than 0.155, then coordination number is 2. So if the radius ratio is less than any value less than 0.155, then radius coordination number will be 2. If the radius ratio reaches 0.155, then coordination number cannot be 2. So any value less than 0.155, coordination number will be 2. But if the value reaches this radius ratio is greater than or equals to 0.155, any value which is equals to 0.155 or greater than this 1.155 but less than 0.225. So radius ratio less than 0.155, coordination number is 2. When the radius ratio reaches 0.155 or greater than but less than 0.225, so we have a range 0.155 to 0.225, coordination number ranges to 3. If the radius ratio reaches 0.225, coordination number cannot be 3, but this will change to another one. So this is 0.225 r plus by r minus, but less than 0.414. So coordination number, radius ratio equals to 0.225 or greater than 0.225 but less than 0.414. So any value less than 0.14 but equal to 0.225 or greater than. So we have a range. If the radius ratio is in this range, the coordination number is 4, that is tetrahedron. If the radius ratio equals to 414 but less than 0.73 equals to or greater than 414 but less than 0.73, coordination number changes to 6, that is octahedral. If the value is equals to 0.73 but less than 1, radius ratio equals to 0.73 or greater than 0.73 but less than 1, then coordination number changes to 8, that is Bode center cubic height. But if the radius ratio equals to 1, coordination number changes to 12, that is FCC type. So once we have this radius ratio, once we define this radius ratio, we can always predict what is the coordination number. Once we know the coordination number, we can also predict what is the type of unit cell. So this is radius ratio. So this is very helpful in finding the coordination number of ionic compound, ionic crystals, provided the size of cation and the size of anion is given to you. So these are the parameters. This is known as radius ratio. This is always in the range. So we have to know the range, and once we define, we can easily predict the coordination number of the cation or anion in an ionic crystal. So for today, we'll conclude here. Hopefully, we enjoyed the class.